In this series of videos, I'm attempting to repair and restore a PDP11-34A vintage computer. In the previous videos in this series, I've been going through the CPU, trying to fault find. There are various faults in it, and there are faults in some of the other cards as well. So what I've been trying to present in this series is the methodology that I use in trying to repair a machine like this. By the way, excuse all the fan noise. I've got various pieces of equipment running, and it will get noisier when I switch on the PDP. Hopefully you can still hear me. So normally when I'm showing repair videos, I don't really show all this legwork that I'm doing, and I skip from point to point and just briefly explain what faults I found. So what I'm doing here is kind of going through the process in almost real time. I'm not really doing much in between the videos. I'm showing you what I'm actually doing to progress through the repair. So it will be a long series of videos, but as I said, hopefully it's not too boring, and for anyone that's interested, it might be useful to do their own fault finding. This is not necessarily the best way of doing this, but it's the method I use. Obviously everyone should use whatever method they prefer. So the approach I take on a piece of equipment like this is to try and get it fundamentally operational, that is, to try and get it at least limping along. And that's what I did. I found a problem with the microcode generator, and I fixed that, so it will now at least try to run through instruction cycles. But it's doing something fairly weird, and I was going over this in the previous videos. So as an example, I'm running a fairly simple test program. So this is just trying to send an incremental value out through the serial port. And what was happening previously is I could read, and just to, before I go into this, the PDP11 it's a very powerful processor, and it's got some features in here that make it more complex than you might first imagine it to be. So we'll come back to that in a few minutes. But one of the things to bear in mind with these machines are that they have a virtual address that we see in the instructions. In this case 177564 is the virtual address for the serial port transmit status register, but the actual hardware is at what is known as the physical address. That's the address that's actually put onto the Unibus, and for in-out devices the virtual address is mapped to the physical address. The actual physical address for this register is 777564, not 177564. So there is a remapping function within the CPU, but it's not quite as straightforward as it might first seem. And what was happening here is the address we saw on the bus for this instruction was correct. We were seeing 777564. But when we got down to this instruction, which in theory should be writing to the next address above this at 777566, what we were seeing was the wrong address. And what we were seeing was this. So we should have been seeing 777566, which is this binary bit pattern. What we were actually seeing was 37566, which is this binary bit pattern. So it looks like the top 4 bits are stuck low, but they're not. And I was kind of hinting at this in the previous video, because the first thing you're going to start looking at maybe is the output for the Unibus. So if you're familiar with these machines, then the it splits everything into 4-bit slices. So the upper 4 bits, for example, are a separate 4-bit slice to the next 4 bits down, etc. And this is true throughout the entire machine. So everything through the ALU, all the circuitry that deals with registers, everything is broken into 4 bits. So when you see something that looks like this, it looks like you've got an issue with one of the 4-bit slices. Now this is kind of misleading, and I kind of did this intentionally because I was trying to show the pitfalls you can get working on a machine like this. The error here is actually the top 5 bits. In fact it's the top 6 bits. It just so happens that the bottom 2 bits coincidentally happen to be correct. And the reason I know this is because I also said it doesn't work at certain memory addresses, and when we look at other addresses, such as trying to replace this address with an address of 2000, which is in the RAM, I was actually seeing 2200 rather than just 2000, so I know that there are other errors in the bit patterns being put out onto the Unibus. But it's not being caused where you might first imagine. So we have these various multiplexers that, depending on the instruction, will manipulate the address that's being calculated. There were some comments suggesting possibly it was an ALU issue where the addition that's being carried out in the instruction, such as here, it's adding 2 as an offset to this address, might be causing a problem. And that is certainly true. That could be the case, but it wouldn't result in exactly what we're seeing here. Also, even if this was writing to the incorrect address, it wouldn't matter. If it's reading from this address but writing to this address in RAM, and this is a valid address in RAM, the actual address we were seeing is valid, that would be fine. Also, there's a red LED on the memory card. You can't see it, but it comes on whenever we get this kind of fault condition showing up. I don't know what's triggering the red LED. I've got a good idea what it might be, but I don't have any technical information on that card, so I'm just guessing. So we're going to start looking at what might be a cause for all this, and obviously using the logic analyzer, I had a bit more of a dig. And it's often easier to try and get the machine to tell you what the issue is rather than starting to probe every single IC. There are 200 odd ICs in this CPU, and it is a very complex machine. So what we're going to do is I'm going to run the test program again, and we'll look at the logic analyzer, and I just want to demonstrate what my thinking is here and what's led me to the conclusion that the fault is not just a straightforward bits stuck on the addressing issue, and I'll come back to that in a few minutes. But it's a fascinating problem we've got here, and hopefully it will become clearer as we go through this video. So I'll just move the camera, and we'll look at the logic analyzer, and I'm just going to run through the test program again, but this time I'll show you a bit more information. Looking at the logic analyzer screen, I have the trigger set to a value of 1002, so the logic analyzer should be triggered on the second line of our program, and in theory, if it was working, it would then go through and start sending data out of the serial port, but of course that's not going to work. So I've got the program entered, I've got the address set at our start address. We'll arm the analyzer, I'll start the program running. You can see we've captured something, but it's halted, the processor's halted, so the analyzer's stopped capturing data because it's in state mode, so the clock has stopped. I'm using the CPU clock on the PDP. So we'll stop the analyzer and see what it's captured so far. So firstly, you can see it triggered at the correct address, and if we look at the data, 012701 is the correct value that we're seeing, so that's the correct address and the correct data value, and the same is true of the next 1004 octal address, and we're seeing a value of 177564, which is correct. That's what the program is. We go on to the next address, 105711, and again that is correct. If we go back to our program, we can see where it says start, that is the correct value. But now it starts going wrong, and this time we're not even reading the correct address here. This was previously working, we were getting 777564. We're now again missing the top, what appears to be the top 4 bits, and instead of being all ones, they're all zeros. But if we keep scrolling across, this is where I'm now going to give you some extra information that will hopefully help start to clarify what the problem is and where it lies. If we keep scrolling across, notice that the next address is 252. If we go back, and this occurs directly after it tries to access this address. So if we go back and look at the test program, this is happening at line where it's given an address of 6. So the instruction is 105711, and it's trying to test a byte pointed to by the value in R1. So in other words, the R1 register contains a pointer to an address location, and that address should be the status address of our serial card transmit register at 777564. But that's failing, it's giving the wrong address, and then when we scroll across, the next address that we hit is 252, and if we keep scrolling across, you'll see that ultimately the address is 250, and that will just keep cycling round. And the 250, the 252 is actually a trap address. It's not a trick address, it's a trap address. If you're again not familiar with the PDPs, they use what they call traps. Really they're kind of system interrupt vectors that are branched to under certain conditions. Now the 250 vector is the memory management vector. So I'm just going to turn the PDP off, it's noisy with the fan running, and I'm going to move the camera. But just remember that what we're seeing here is a branch to address 250 as a result of us reading a specific address. Then that address is incorrect. In fact, before I move the camera, what I'm going to do is change the target address. So instead of it being, as we can see here, 177564, I'm going to change it to 2000. And this is just to clarify a point I made earlier. So I'm just going to change the program. Okay, so I've now got the target address set at 2000, which is a valid memory location in this system. So what I'll do now is we'll rearm the analyzer, and I'm going to try and rerun the program. So again, it's stopped, and we'll stop this and we'll scroll across. You can see now that the address is 2000, and that's showing correctly, so it is reading in the correct data value. And when we go across, you can now see that the address that we're hitting is 2200. This is what I meant earlier about it's not just the top 4 bits that are incorrect. It's actually the top 6 bits of the address. That's the not the virtual address, but the physical address. The top 6 bits are incorrect. So it should be 2000. It's showing us 2200, so that's the wrong address again. And again, we are then branching to the memory management error trap vector. So, okay, we'll try and figure out now what's going on. I'm going to move the camera and we'll try and have a think about what may be causing this. Okay, in fact, before I do that, I'm just going to make one change. I'm going to change the value in some registers in the PDP. I'll come back to what these registers are in a few minutes and explain what they're for. But the point here is you can see that we are vectoring to 2200 rather than 2000. But I'm just going to change the value in a few system registers. I'm not changing the program here, so I'll do that and then we'll try running the program again. Okay, I've changed the value that's in 16 system registers within the PDP. As I said, I'll come back to what they are in a few minutes. But I'm going to rearm the analyzer. Remember that we vectored to 2200 and it should have been 2000. I'm going to try and run the program again. And it's halted. We'll stop. But this time notice that we are going to the correct address at 2000. However, it's still not running. If we scroll across, you'll see we're still hitting the memory management error. So what I'll do is move the camera now and I'll just try and explain what I think is going on here. So when you first see a fault like this, where certain bits, especially where it appears initially that blocks of 4 bits are not being set correctly, it's very tempting to jump to the conclusion that you've got an error in maybe part of the circuitry like this, and it's one of these blocks of 4 bits that's at fault. But as I said, I don't believe that's what's going on here. Now I'm doing this in real time, so I don't know any more really than you've seen. I'm just speculating as to what I believe may be causing the problem. If you're familiar with these and you've seen this sort of problem before, then please leave a comment. But what I believe is causing this is an error in the memory management system. If you're not familiar with the memory management in the PDP machines, you can think of it almost like a combination of the paging you get in something like a PIC microcontroller and the old memory ring management and protection you get in the Intel 80386 processors. And I also mentioned in a previous video that quite often you can have faults in machines such as the PDP that you're not aware of, and they only come to light when you carry out certain testing. And this is a good example of that. There's a lot of circuitry in the PDP11-34 that is just for memory management, but you don't need to use the memory management. It's used in operating systems and higher level software. But when you first boot up the PDP, the memory management should be off. It should be disabled, and you can test that. If you look at the there's a register, or should be a register within the CPU that controls whether that memory management system is active or not active. And if we have a look at that, it's at address 175572. And if we look at it, to disable memory management, you set this address value to 0. And if we examine it, it is 0. And in fact, anytime you use a control start or control boot, it sets this register to 0, because when you boot up or start a program, it always starts in non-memory managed mode. That mode is only really for operating systems, because it requires the 16 registers I mentioned to be loaded with valid values. If they've got nonsense in them, then the system won't work if you try and enable memory management. So the memory management registers are held in this part of the circuit, and really what these are 4x16-bit flip-flops or latches. And so really you can look at these as if they're just RAM chips, low capacity RAM chips. And there's two sets of them, but they need to be loaded with valid values. Now, one set of these is to hold vectors, and the vectors are what are effectively added to the virtual address to result in the final physical address. That is, you can map any virtual address, and it's in 4K blocks. You can map any one of those blocks to any physical address that you want in memory management mode. And on top of that, you can also set specific restrictions for each of those blocks, whether you can not access it at all, whether you can write that block, or whether you can read it but not write it. And that's kind of what we're seeing. It's almost like the system's not being allowed to access the vectors it wants to. Now, if any of these memory management tasks fail, then there's another circuit I won't show you. It's quite complex, but there's another part of the circuit that detects that as an error, and it throws an error, and the result is that it will vector to address 252, and again there should be a handler vector. So what systems normally do, operating systems, is they will load a branch vector at address 252, and what should happen is when this fault occurs, the system will vector to 252. 252 in RAM will contain an address that the CPU then branches to handle the error. That can't happen here because we don't have an operating system loaded, and in fact the memory management shouldn't be active at all. This is the memory management register, that's the one we just checked, and it is 0, so the memory management should be disabled. So none of this should be happening. It shouldn't be modifying the addresses, and we know it's coming from here because the register I modified that changed the vector or the address we ended up at. That's the physical address we went to, so it went from 2200 to 2000. The only thing I changed was the vector in the memory management register, but it should have had no effect because memory management is disabled, so it shouldn't be doing anything at all. All this should be inactive. And we can kind of back this up. The scope, I've got these two scope probes hooked up to the error output of the memory management system, so there's a signal that toggles whenever an error occurs within memory management, and also another one that is used to trigger the relocate signal, which again, neither one of those should be active when the register we looked at is set to 0. So what we'll do now is, if you watch the scope, I'm going to try and start the program. So we'll go to the start address, I'll try and run it, keep an eye on the scope. Notice that we're getting both signals pulsing and neither one should do anything. We'll try that again. So again, and that's an indication that the memory management error detection is being triggered, and again it should be inactive. It should not be being used to change our target address. The only thing that should happen with the memory management disabled is we should use the raw virtual address that we read as part of the program. That was the 177564, and it should map that directly to 777564. It should not start adding memory management vectors to our target address. So, and also it should not be triggering the memory management error because that should be turned off. So I believe that the problem is either the memory management circuit, such as this area here, is giving an output that indicates it's active when it shouldn't be. So it could be as simple as this gate here is not working. I haven't tested it yet. That's what we're going to come to in the next video. Or it could be something more complex within the system that's causing the memory management to kick off when it should be inactive. Okay, so hopefully this is starting to make some sense and you're seeing the reasoning behind what I'm doing, and also that it's clear this is not a simple case of 4 bits stuck within the address calculation or output. You can force it to give the correct address by manipulating the vectors that are stored in these registers. I said it shouldn't have any effect, but it does, and you can get an output of the address that you want by putting in the correct vector values. It's still not working because it still throws up the memory management error vectors to the memory management error vector and then crashes because there's no handler there, and that's why the CPU is stopping. And it's also one of the reasons why the system is so flaky and it's varying, because every time I boot the system up it has different values in these registers. What's in here, they're not preloaded unless you boot to an operating system. What's in these when you boot up the system is just kind of almost random data, and because it's got random data but it's trying to use them as vectors, then it just crashes the system. So in the next video we'll start trying to fault find this, try and figure out why the memory management system is active when it shouldn't be. It's complicated by the fact that I know there are other errors and faults in this system, but we have to start somewhere, and getting the memory management to effectively mind its own business until we want it is going to be our next step. As I said, unfortunately there's a lot of things that can cause this to happen. But we'll start at the memory management control register and work our way forward and see why memory management is getting involved in this simple test program.